Welcome to the fourth episode of my exercise series Introduction to Physics. And I have to start with a confession. Even though I like going to fun fairs, I'm not a huge fan of roller coasters. But today we will use this example, the roller coaster, to calculate forces and motion. So let's get on with it. At a fun fair, a car glides from a height h down without friction on an inclined plane and then makes a loop of radius r. What forces act on the car in multiples of weight force g at the lowest and the highest points of the loop when the car starts at a height twice the loop diameter? What starting height must be selected so the car can make its way through the loop without losing contact with the road? Again, as always, let's find out what values are given and what are we looking for. First of all, the given variables. We have given the height h, of course in this case without any real values, but still it's given. And we've given a radius r. And we know in particular that the initial height is twice the diameter, which means the height h is 4 times the radius. And we are searching for the force in point A, the lowest point, and point B, the highest point of the loop. And in addition, we are looking for the height h in case that the sum of all forces in point B, FB, equals to 0. So let's make a little sketch. You can see here the inclined plane, and right after the plane we have this loop. We are starting on the left-hand side in a certain height h that was given as 4 times r. So the car glides down and goes through the loop, first in the lowest point and then in the highest point. And we are looking first of all for the forces in point A and point B. How do we go at this task? What are the forces in point A? Of course, we do have the gravitational force. The gravitational force always points downwards. And we can calculate it as G equals m, the mass of the object, in this case a car, multiplied with the gravitational constant g, which is equal to 9.81 meters per second squared. But since we are going to look for the result, the sum of all forces in multiples of the gravitational force g, we do not need any values right here. Do we have any other forces? Yes, of course. We are talking about an object that goes through a loop. So there is, in addition to the gravitational force, also the centrifugal force. And the centrifugal force always points outwards. And outwards in this case in point A means it also points downwards. So we have the centrifugal force Fz equals m times velocity squared divided by the radius of the loop. Then the total force is simply the sum over the gravitational and the centrifugal force, and we can take our two equations above and put them into one equation and calculate the total force in point A, Fa equals mg plus mv squared divided by r. So yes, we have solved the problem at this point. We are supposed to give our results in multiples of our gravitational force. So on the right-hand side of our equation, the second term, it's still a bit different. It's not really multiples of m times g. So we have to rewrite this part of the equation. How do we do this? Well, there is a velocity in point A that we don't know anything about it at this point. How can we calculate it? Well, when we think about it, we are still in the field of point masses here. And talking about a point mass that comes down from a certain height and has lots of potential energy and transfers all this energy when it comes to the lowest point into kinetic energy, we can think about energy conservation. And in case of energy conservation, all the potential energy from the initial part, from the start, equals the kinetic energy in point A. Then we just need to say, what are the energies? Well, potential energy is always calculated as the product of mass, gravitational constant, and height. And the kinetic part of our equation is mass divided by 2 multiplied with the velocity squared. You can see we have the mass m on the left hand side and on the right hand side, so we do not need it. And everything that we want is the velocity actually, and velocity squared equals 2 times g times h. And we can put this into the equation of the forces. And this results in a simplified equation where we have indeed mass and gravitational constant in both terms on the right hand side. And in addition, you can see here that we need to know something about the height where we start and the radius of the loop. But we know that the starting height equals 4 times the radius. So in the second term, the radius cancels out, and we get finally that the forces in point A equals 9 times the weight force. And of course, the total force is directed downwards. Secondly, we were also looking for the forces in point B. Now, of course, again, here also we do have the gravitational force because nothing has changed and it's still pointing downwards. So G equals mass multiplied with gravitational constant. Of course, there's also still the centrifugal force, but since the centrifugal force always points outwards in a loop like this, in this special case in point B, it's actually pointing upwards. So we have to take a minus into consideration such that Fz equals minus mass m multiplied with velocity squared divided by the radius. And yes, this is not the only problem. Of course, the total force is just the sum over those two forces, and we do have to take the minus into consideration right here. But we cannot take the velocity that we already calculated and just reuse it. Because energy conservation in this special case tells us that the initial potential energy, yes, part of it goes into the kinetic energy, the energy of motion in point B, but point B has also a certain height above, say, the ground level. So we need additional term, the potential energy in point B. But this is not too complicated. On the left-hand side, we have the product of mass m, gravitational constant g, and height h. On the right-hand side, of course, we do have the kinetic energy m divided by 2 multiplied with the velocity that we need squared, plus m times g times the height. And the height in point B is simply 2 times the radius, or the diameter. Does this help us? Yes, of course. We wanted to know the velocity in point B. And since we can see here that we still have the height h and the radius r in our equation on the right-hand side, we know that the height h equals 4 times r. We can make a very simple equation out of it. We know that the velocity in point B squared equals 4 times g times r. And if we put this in our equation of forces, we can see here that on the right-hand side, our radius r cancels out again, which enables us to tell that the total sum of forces in point B equals minus 3 times the gravitational force, the weight force. And the minus tells us that in this case it's directed upwards. Let's have a short look back on the variables we are searching for, and we see that yes, we've calculated FA and FB, but we are still searching for the height that we have to choose initially, such that the total sum of forces in point B equals 0, which means that we are actually not losing contact to the loop. But this is relatively easy to calculate because the force is 0 times the weight force. So FB equals 0 in this case, which means nothing new than that the weight force equals the centrifugal force. And of course, it's a new centrifugal force. So therewith, we can use the basic equations for weight force G on the right-hand side as m times G, and on the left-hand side for the centrifugal force, m multiplied with velocity squared divided by radius r. And of course, we still have energy conservation, and we can calculate the velocity from energy conservation in, say, the most general form. So we've seen already that the velocity squared in point B equals 2 times gh minus 4 times gr. And now in this particular case, we do not know anything about the relation of height h to radius r. This is exactly what we want to calculate. So let's take v squared and put it in our equation of forces, and what we get is shown here. We've got on the left-hand side mass m multiplied with 2gh minus 4gr, divided of course by the radius r, and on the right-hand side we've got the product of mass m and gravitational constant g. So what is the result? Well, first of all, we can divide this whole equation by m, the mass, it cancels out. Then we can divide it by the gravitational constant g, which is part of every term of the equation. And what we get is simply that 2 times height h minus 4 times radius r equals radius r if we multiply the previous equation with r in addition. This also means that the height h that we have to start with initially equals 5 divided by 2 times the radius. This means that if we are starting at a height of 2.5 times the radius, assuming there is no friction, we will get through the loop without losing contact. And with this, I hope that when you go to a fun fair next time, you can actually calculate the forces that hit you during riding a roller coaster. But please take the friction into account when you calculate it before you hop on, because this can make actually a huge difference. And with this, I would like to thank you for your kind attention, and I hope it helps you to prepare yourself, for example, for an exam. And if it helped you, please give me a thumbs up, and I would be very happy if you subscribe, and I'll see you for the next video. Bye!